During the chaotic early stages of a system's formation, countless solid bodies move along intersecting paths. When two sizable objects meet at high speed, the resulting impact can alter their structures in dramatic ways. Mountains can melt, oceans can vaporize, and crusts can be shattered. Some collisions merge the bodies into a single larger world, while others tear them apart, scattering fragments across the system. These fragments may later reassemble into moons, rings, or smaller companion bodies. The heat generated by such impacts can create global magma oceans that reset a planet's surface entirely. Evidence of ancient collisions is preserved in cratered landscapes, unusual rotations, and unexpected compositions. By studying these scars, researchers reconstruct the violent histories that shape the planets we see today. Each collision leaves an imprint that reveals how even stable-looking worlds are the products of intense and transformative events. Rings around distant planets can stretch wider than the distance between Earth and the Moon. These enormous structures form when material becomes trapped in orbit around the planet, rather than merging into a single moon. Dust, ice, and fragments of rock circle in countless individual paths, each grain responding to gravity and tiny collisions with its neighbors. The brightness and texture of a ring system depend on the size and composition of its particles. Some rings shine softly with fine icy grains that scatter starlight, while others contain darker fragments that absorb more light and appear faint, even when they span incredible distances. In young systems, collisions between forming moons can produce fresh debris that spreads into broad arcs. Over time, gravitational interactions carve the rings into narrow bands, gaps, and waves, creating patterns that shift gradually as the orbits evolve. When astronomers observe rings around distant worlds, they see more than beautiful structures. They see evidence of ancient impacts, migrating moons, and the subtle forces that shape entire planetary systems. These vast rings show how dynamic and varied worlds can be, even when they lie far from the warmth of their stars. Some stars orbit each other so closely that they share outer layers of gas. In these extraordinary binary systems, two stars form so near each other that their gravitational fields overlap. As they evolve, one may expand into a swollen giant whose outer layers spill over toward its companion. The flowing material forms a bridge between the two bodies, creating a swirling region where gas circulates. Under the tug of both stars, this exchange can dramatically alter their fates. The receiving star gains mass and grows hotter and brighter, while the losing star becomes stripped and can reveal deeper layers that would normally remain hidden. The shared atmosphere can generate complex patterns of heat and motion, leading to eruptions, flares, or pulses of radiation that vary over regular intervals. Observing these systems gives astronomers a unique view of stellar evolution, because the stars influence one another in ways that solitary stars never experience. Their intertwined lives demonstrate how companionship in the cosmos can produce outcomes far more dramatic than either star could achieve alone. Dense globular clusters can pack hundreds of thousands of stars into tight spheres. These ancient collections orbit the outskirts of galaxies like glittering beacons of stellar history. Each cluster contains stars that formed at nearly the same time, making them some of the oldest surviving structures in the universe. Because they are so densely packed, the stars within them lie far closer together than the stars in typical regions of a galaxy. In such crowded conditions, gravitational encounters are frequent. These encounters can fling stars outward, draw others inward, and alter orbits in ways that create a constantly shifting internal environment. Some of the stars found in globular clusters are unusually blue and bright because they are thought to have formed through mergers or mass transfer events triggered by those close interactions. The clusters maintain their tight shapes because their combined mass keeps the stars bound together despite the constant motion. Studying them reveals how early star formation unfolded and how nature preserves these ancient spheres across cosmic time. The interstellar medium can carry shockwaves from ancient supernova explosions. When a star explodes, the blast sends out a powerful front of energy and material that sweeps through surrounding space. Although the interstellar medium appears thin, it contains gas dust and charged particles that can be pushed and compressed by these waves. As the shock travels onward, heats the material it encounters, sometimes triggering new chemical reactions or exciting atoms to glow in characteristic colors. These waves can continue expanding for millions of years, shaping the structure of nearby clouds and influencing the birth of new stars. The effects ripple outward across immense distances, leaving behind shells, bubbles, and filaments that mark the path of the ancient explosion. By examining these patterns, astronomers can estimate when the original supernovae occurred and how much energy it released. Each shockwave becomes a messenger from a long-vanished star, carrying information across space. In the subtle changes it imprints on the interstellar medium, some planets orbit so rapidly that their years last only a few Earth days. These worlds circle their stars at such close range that gravity pulls them along dizzying paths. With each swift orbit, they experience intense radiation and dramatic temperature swings. Those surfaces or atmospheres face challenges no planet in our solar system encounters. On the star-facing side, heat can build to levels that melt rock or vaporize minerals. On the far side, temperatures can plunge sharply unless powerful winds distribute heat efficiently. The quick pace of each orbit creates unique atmospheric patterns as currents struggle to keep up with the rapid cycle of day and night. Some of these planets are locked so that one side always faces the star, intensifying the contrast between scorching light and deep darkness. By studying these extreme environments, scientists learn how planets respond to conditions far beyond those on Earth. Their short years and blistering climates expand our understanding of worlds can become. Spiral galaxies can grow new arms as they interact with neighboring systems. The graceful spirals that define these galaxies may appear stable, yet their shapes are influenced by gravitational forces from surrounding objects. When another galaxy passes nearby, even without direct contact, its pull can disturb the distribution of stars and gas in the spiral. Waves of density can propagate through the disk, compressing material into arcs that gradually curve into new arms. These arms are not rigid structures, but patterns where stars bunch together for a time before drifting onward. Gas within the arms becomes denser, encouraging the formation of bright young stars that enhance the spiral appearance. Over millions of years, repeated interactions can reshape the entire structure of the galaxy. In some cases, new arms emerge, while older ones fade or twist into distorted loops. Observations of such transformations reveal how galaxies evolve through encounters and how the cosmic environment influences their long-term development. Massive star clusters can light up the surrounding gas with intense ultraviolet radiation. Clusters containing many hot young stars produce significant amounts of high-energy light that streams outward in all directions. When this radiation meets nearby clouds of hydrogen-rich gas, it strips electrons from the atoms and heats the cloud. The gas then glows with a distinctive set of colors that reveal its composition and temperature. The surrounding region becomes a bright nebula with tendrils and shapes carved out by the forces at play. Winds from the stars push the gas outward, while the radiation sculpts pillars, ridges, and cavities. Over time, as the cluster evolves, the brightest stars burn out, quickly leaving behind a changing landscape of light and shadow. These illuminated regions help astronomers trace how star formation progresses within clusters and how young stellar communities influence their environments. The brilliance of these regions showcases the power that even a single cluster can exert on the cosmic neighborhood around it. Rogue stars can travel at immense speeds through intergalactic space. These solitary travelers are thought to have been flung out of their home galaxies by gravitational encounters that gave them incredible momentum. Some may have passed too close to a supermassive black hole, while others were ejected during complex interactions among multiple massive stars. Once expelled, they raced through space with no galaxy to call home. Their paths take them into regions where starlight is faint and matter is sparse, making them difficult to detect. However, their speeds and trajectories reveal clues about the events that launched them. By measuring their motion, the strongness can trace back to the violent moments that set them free. Though isolated, these stars carry with them the chemical signatures of their origins, offering insight into the environments from which they came. Their journeys remind us that even stars can experience dramatic displacements that send them wandering across the great emptiness between galaxies. Some planetary systems form multiple asteroid belts that resemble cosmic rings. During the early stages of formation, leftover material from the birth of planets can remain in stable orbits around a star. These belts consist of countless rocky fragments ranging from tiny grains to substantial bodies. Over time, gravitational influences from planets sculpt the belts into separated regions rather than continuous fields of debris. The gaps between the belts form where resonances disrupt the orbits, clearing paths that remain empty. Each belt reflects the history of its system, showing how collisions, migrations, and gravitational shaping have distributed the debris. The presence of multiple belts suggests a complex past with interactions that influenced how planets settled into their current positions. Observing these structures in distant systems allows astronomers to compare them with familiar features like the asteroid belt and the Kuiper region of our solar system. These comparisons deepen our understanding of how planetary systems evolve and how debris patterns reflect their early history. Quasars can shine with the power of trillions of stars combined. These extraordinary objects reside in the hearts of young and active galaxies, where vast amounts of gas spiraled towards supermassive black holes. As the material falls inward, it forms a disk that heats to extreme temperatures from friction and compression. The disk radiates across the Chi electromagnetic spectrum, producing enormous luminosity that outshines the entire galaxy surrounding. Clouds absorb and remit the radiation, creating strong spectral features that reveal the physical conditions near the core. Despite their brilliance, the central regions fueling the quasar remain incredibly compact. The energy output depends on the rate at which matter falls inward, and this process can vary over time. Observations of quasars at different distances show how these energetic objects were more common in the early universe, reflecting a period when galaxies were rapidly growing and feeding their central black holes. The immense power makes them visible across great cosmic distances. Astrobiologists study planetary atmospheres to search for chemical hints of life. To understand whether a distant world might support living systems, researchers examine the gases surrounding it with extraordinary care. When starlight passes through a planet's atmosphere during an orbit, the light carries subtle imprints created by the molecules it encounters. Sensitive instruments can separate this light into its component colors and reveal the presence of substances that may indicate biological activity. Oxygen, methane, and other reactive gases are especially interesting because they should vanish quickly unless something replenishes them. On Earth, living organisms maintain many of these gases through constant interaction with the environment. Astrobiologists combine atmospheric models, laboratory experiments, and observations across many wavelengths to determine whether unusual chemical mixtures could arise from natural processes alone, or if they might require something more dynamic. That work demands caution, because planets can produce surprising chemistry without life. Even so, each newly analyzed atmosphere adds to a growing library of possibilities. This expanding knowledge helps refine the search for planets that might host stable climates, liquid water, and long-lasting cycles that could support. Biology informs familiar or unfamiliar. The surfaces of some moons are constantly reshaped by cryovolcanic eruptions. These moons contain interiors that remain warm enough to keep certain materials melted beneath their icy crusts. Instead of molten rock, their hidden reservoirs contain mixtures of water, ammonia, nitrogen, or other volatile substances that remain liquid at low temperatures. Pressure builds as these subsurface oceans and chambers shift and churn. When pathways open through cracks or weak points in the ice pressurized, Material escapes in plumes that rise into space or cascade across the surface. Over time, these eruptions create smooth plains ridges and mottled textures that replace older terrain. The resurfacing process can hide impact craters and erase geological features that would otherwise preserve a long history. Observing these ever-changing landscapes teaches scientists how internal heat tidal forces and complex chemistry maintain activity. In worlds far from their stars, the presence of liquid environments beneath the surface also raises profound questions about what might exist in these protected, energy-rich habitats. Gravitational lensing can magnify galaxies so distant that they would otherwise be invisible. As light travels across the cosmos, it moves through regions shaped by the distribution of mass. When a massive object lies along the line of sight between the observer and something far beyond the curvature of space around that, mass alters the path of passing photons. The effect can stretch, brighten, or multiply the appearance of the background galaxy. Instead of a single faint smudge, the observer may see arcs or wings that trace the bending of the light. This magnification allows astronomers to study structures that formed when the universe was young, revealing details about star formation, dust content, and the assembly of early galaxies. By analyzing how the light is distorted, researchers can map the mass within the lensing object, including any dark matter that emits no light. Each lensing event becomes a natural telescope built by gravity itself, offering a rare view of regions too distant for direct observation. Young stars can flicker unpredictably as dust clouds drift across our line of sight. In stellar nurseries, where stars begin their lives, gas and dust remain abundant. Young stars often possess swirling disks of leftover material that will one day form planets, moons, and smaller bodies. Clumps within these disks can pass between the star and the observer, blocking or dimming the light. The resulting fluctuations may follow no obvious pattern because the dust distribution is constantly shifting under the influence of winds, magnetic fields, and gravitational forces. Some stars dim slowly and brighten quickly, while others show a chaotic sequence of changes. These patterns offer clues about the structure and behavior of the disks surrounding them. By studying the flickering, scientists can detect rings, gaps, warps, and regions where material accumulates. The variations also help identify potential planets forming within the disks as their gravitational effects shape the dust. These early changes reveal the dynamic environment in which solar systems take their first steps toward maturity. Some galaxies grow by steadily consuming smaller companions. Galaxies do not always evolve in isolation. In crowded cosmic neighborhoods, large systems frequently encounter smaller ones. Gravity pulls them together, slowly causing the smaller galaxy to lose stars and gas as it spirals inward. Streams of material stretch out behind it, leaving luminous trails that mark the path of the cosmic meal. These mergers can trigger bursts of star formation as gas clouds collide and compress over long periods. The larger galaxy incorporates the stars of its companion, adding to a halo and inner regions. The chemical signatures of these absorbed stars differ slightly from those already present, allowing astronomers to trace the history of past mergers. This process of gradual growth plays a major role in shaping the structure of galaxies and helps explain why many exhibit complex layers, extended halos, and subtle variations in stellar populations. Each consumed companion becomes part of a larger whole, its identity preserved only in faint remnants. The atmospheres of some exoplanets glow faintly as they heat up in starlight. When a planet orbits close to its star, intense radiation warms its atmosphere to temperatures far higher than anything found on Earth. The excited molecules and atoms remit energy in the form of a delicate glow that can be detected at infrared or visible wavelengths. This emission reveals details about the gases present, their temperatures, and the dynamics of the atmosphere. In some cases, the glow shifts across the surface as winds redistribute heat from the day side to the night side. Certain planets display chemical reactions triggered by ultraviolet light, producing compounds that contribute additional brightness. By observing these faint emissions during different phases of the orbit, scientists reconstruct weather patterns, thermal gradients, and atmospheric circulation on worlds that remain unresolved to single points of light. The soft radiance that surrounds these planets offers a window into environments shaped by intense stellar energy. Planetary nebulae mark the final breaths of medium-sized stars. When stars similar in mass to the Sun reach the ends of their lifetimes, they shed their outer layers through slow winds and gradual pulsations. As the layers drift outward, the hot core left behind illuminates them with ultraviolet light. The gas responds by glowing in vivid colors that trace the composition and density of the expanding shell. These shapes can become rings, ovals, or intricate patterns, depending on the stars, rotation, magnetic fields, or interaction to other companion. A nebula expands over time, gradually thinning until it fades into the background of interstellar space. The exposed core cools and becomes a compact remnant that will shine faintly for billions of years. Planetary nebulae provide valuable insight into how stars recycle material back into the galaxy, enriching future generations of stars and planets with heavier elements. Each one represents a transition from active stellar life to a quiet final stage. Supermassive black holes can regulate star formation across entire galaxies. At the centers of many galaxies, enormous black holes gather material into swirling disks. When the inflow becomes vigorous, the region near the core releases tremendous energy that travels outward through jets, winds, and radiation. These outflows heat surrounding gas and can push it away from the central regions. If the gas becomes too warm or too diffuse, it cannot collapse to form new stars. In this way, the central black hole influences the pace of growth across the entire galaxy. Galaxies with very active centers often show reduced star formation in their inner regions, while those with quiet centers may continue forming stars at a steady rate. This connection reveals a delicate balance between feeding the central black hole and allowing the galaxy to build new stellar populations. Understanding this relationship helps explain why galaxies differ in appearance, behavior, and long-term evolution. Some stars orbit the galactic center on paths tilted far above the Milky Way's disk. Most stars follow orbits that stay within the thin disk of our galaxy, but a significant number travel on paths that rise high above or dip far below it. These tilted orbits can result from ancient interactions, mergers with smaller galaxies, or gravitational disturbances caused by massive objects. As stars move along their inclined paths, they offer a three-dimensional view of the galaxy's structure. Their motions help astronomers map the distribution of mass, including dark matter that cannot be seen directly. Some of these high-flying stars may be remnants of long-absorbed dwarf galaxies, preserving chemical signatures that differ from the disk population. Their unusual orbits reveal the dynamic history of the Milky Way, showing how past events shaped a structure that now appears stable and serene. Shock waves from supernova can trigger new waves of star formation. When a massive star explodes, the expanding blast pushes into surrounding molecular clouds. The shock compresses the gas and dust, increasing the density in regions that were previously too diffuse to collapse. If the compression reaches a critical threshold, gravity takes over and the cloud begins to contract. New stars begin forming in the wake of the explosion, turning destruction into creation. This process helps renew regions of the galaxy and contribute to the cycling of material between generations of stars. By observing these triggered sites, scientists can follow the train of events linking the death of one star to the birth of many others. The timing, shapes, and locations of these new clusters provide clues about how the shockwave traveled and how far its influence extended. These interactions illustrate the interconnectedness of cosmic processes, where the end of one stellar life becomes the spark for countless new beginnings. Some binary stars are so close that one pulls material off the surface of the other. In these remarkable systems, the two stars orbit each other at such short distances that their gravitational fields overlap in a delicate but powerful balance. As one star expands during its evolution, its surface can swell beyond the region where its own gravity remains dominant. When this happens, gas from the outer layers drifts toward the companion, forming a flowing bridge of material suspended between them. The receiving star often gathers the falling gas into a spiraling disk that grows hotter and denser as more material arrives. This transfer can dramatically alter both stars. The donor becomes stripped and reveals deeper layers that would normally stay hidden while the companion grows in mass and luminosity. Sudden bursts of brightness can occur when the accreted gas heats rapidly or undergoes explosive reactions. These complex interactions help scientists understand how close companionship can reshape the lives of stars in ways that solitary stars never experience. Cosmic dust grains can contain crystalline structures forged in dying stars. These tiny particles travel through interstellar space, carrying the signatures of the environments where they formed. In the outer layers of aging stars, gas cools and condenses into solid grains as the star sheds material into its surroundings. Under the right conditions, atoms align themselves into orderly repeating patterns that create crystals with unique chemical fingerprints. Supernova blasts and powerful stellar winds then scatter these grains across the galaxy, mixing them into clouds that will eventually form new stars and planets. When scientists analyze the light reflected or absorbed by dust, they detect subtle features that reveal the presence of these crystalline structures. Some grains are older than the solar system itself, making them relics of long-vanished stars. Their composition helps trace the cycle of material from one generation of stars to the next, showing how the universe continuously recycles the building blocks of Thothi, planets, and possibly even the ingredients for bi-life. Stellar nurseries can form intricate networks of filaments filled with newborn suns, with intense clouds of gas and dust. Gravity gathers material into long strands that weave through the darkness like luminous threads. These filaments act as natural highways for matter to flow into regions where stars are beginning to form. As gas accumulates, knots develop along the filaments, each one gradually growing hotter and denser. Eventually, these knots collapse and ignite as young stars surrounded by swirling disks of leftover material. The filaments themselves may twist and bend under the influence of magnetic fields and turbulent motion, creating a tapestry of shapes that changes slowly over time. Observations at multiple wavelengths reveal how material moves through these networks and how different temperatures highlight distinct structures. These nurseries provide a view of the earliest stages of stellar development, showing how interconnected processes create entire clusters rather than isolated stars. Each glowing thread marks a pathway through which the galaxy continues to renew itself. Some planets develop thick atmospheres of hydrogen that dwarf their rocky cores. These enormous envelopes form when a young planet grows rapidly, enough to capture light gases before the surrounding disk disperses. Hydrogen and helium flow toward the growing world and accumulate in quantities far exceeding the mass of the rocky material beneath. Over time, the atmosphere becomes a vast layer extending high above, the core blending continuously from dense lower regions into the thin outer edges. Temperatures and pressures inside this envelope can reach extreme levels, producing exotic forms of chemistry not found in smaller planets. Winds move through the atmosphere at tremendous speeds, carrying heat from one region to another and creating dynamic weather patterns that may span the entire planet. Even though the rocky core remains hidden from view, the atmosphere reveals much about the planet's history and environment. It preserves clues about the early stages of formation, helping researchers understand how planets grow and why some accumulate far more gas than others. The chemical fingerprints in Starlight can reveal the composition of distant worlds. When the planet passes in front of its star, a portion of the starlight filters through the planet's atmosphere before reaching observers. Each type of atom or molecule absorbs specific colors of light, leaving a series of subtle but distinct patterns in the spectrum. By analyzing these patterns with sensitive instruments, scientists can infer the presence of gases that may hint at climate, weather, or even geological processes. The technique works even for planets that cannot be directly imaged, allowing researchers to explore worlds far smaller and cooler than previously possible. As data accumulate, comparisons between different planets reveal trends in atmospheric chemistry that reflect formation history and environmental conditions. These fingerprints provide a method for examining worlds across the galaxy, using nothing more than the light they allow to pass through. This approach represents one of the most powerful tools for studying distant atmospheres, without sending probes or missions to the worlds themselves. Relics of ancient galaxies remain scattered throughout the Milky Way. Long ago, smaller galaxies drifted close enough to the Milky Way for gravity to seize them. Instead of surviving intact, many were slowly torn apart as they spiraled inward. The stars stretched into elongated streams that wrap around the galaxy like faint trails of stardust. These remnants remain visible as thin ribbons of light that trace the orbits of the long-consumed systems. Each stream carries a distinct chemical signature that differs from the stars born within the Milky Way, allowing astronomers to identify their origins by mapping their paths. Researchers reconstruct the merger events that shaped our galaxy over billions of years. Some relics appear as faint clusters still holding together, while others have dispersed into the broader halo. Together, they form a historical record preserved in Starlight, revealing how the Milky Way grew by, gradually absorbing its smaller neighbors. Some stars are surrounded by dusty disks left over from planet formation. After planets form within swirling disks of gas and debris, leftover material often remains in orbit around the star. Collisions between smaller bodies continually grind fragments into fine dust that spreads across the system. This dust absorbs starlight and remits it at longer wavelengths, creating a signature that can be detected with specialized telescopes. The structure of these disks varies depending on the presence of planets, which can carve gaps, shepherd rings, or scatter material into new configurations. Observing the distribution and temperature of the dust reveals the architecture of the system and helps identify regions where planets might still be forming. Over time, radiation pressure and collisions gradually remove the material, but some disks persist for hundreds of millions of years. These dusty rings act as archives of early planetary history, offering clues about the processes that shaped the worlds. Orbiting the central star, intergalactic gas can stretching narrow filaments that connect distant clusters across the universe. Matter is not evenly distributed. Instead, it collects into vast structures that form a cosmic web of clusters, nodes, and connecting strands. These filaments consist of diffuse gas enriched with elements forged in earlier generations of stars. Though extremely faint, they span enormous distances and help channel material into growing galaxies. Observations reveal that these filaments guide the motion of galaxies and influence how clusters evolve as gravity pulls matter along the strands. Interactions between gas and dark matter shape the growth of large-scale structures. Studying these filaments requires sensitive instruments that can detect subtle signals from hot or ionized gas. Their existence confirms theoretical models of cosmic evolution and demonstrates how the universe organizes itself on the largest scales. Through them, galaxies receive the raw material needed to form new stars and continue expanding their stellar populations. Cosmic magnetic fields can influence the motion of charged particles across huge distances. These fields arise from the motion of conductive plasma within stars, galaxies, and intergalactic gas. Once established, they create invisible pathways that guide the movement of electrons and ions. Charged particles spiral along the magnetic lines, often traveling great distances while emitting radiation that reveals their presence. The strength and orientation of these fields vary from place to place, shaping the behavior of cosmic rays and affecting the structure of nebulae and jets. In regions with complex magnetic activity, particles can become trapped in loops or channeled into narrow beams that stretch far from their origins. Understanding these interactions helps astronomers trace the flow of energy in environments where gravity pressure and magnetic forces all play significant roles. The influence of magnetic fields demonstrates how even unseen forces contribute to the dynamics of the universe. Some planets orbit dead stars that emit little more than faint ghostly light. When a star of moderate mass completes its life cycle, it sheds its outer layers and leaves behind a compact remnant that slowly cools over time. These remnants produce only a dim glow yet. Some continue to host planets that survive the dramatic transformations of their parent stars. The faint light offers minimal warmth, creating environments far colder than those around ordinary stars. Any surviving planets may have experienced intense heating during earlier phases, followed by long periods of deep freeze as the stellar remnant faded. Some planets might orbit so closely that they experience strong tidal forces, while others drift farther out in the cold. Studying these systems reveals how planetary bodies endure extreme changes and adapt to evolving stellar conditions. The continued existence shows that planets can persist even after their stars cease shining brightly. The atmospheres of some gas giants glow in infrared wavelengths. Deep within these enormous worlds, heat rises from the interior and escapes through thick layers of gas. Much of this heat is released as infrared light that is invisible to human eyes, but detectable by specialized instruments. The glow forms because the gases in the atmosphere absorb energy and later release it as gentle radiation. This steady output can reveal the temperature's motions and chemical makeup of the atmosphere. Winds carry heat across the surface, shaping patterns that shift slowly over time. In some giants, storms stir the gases so deeply that warm regions rise from the interior and shine more brightly than their surroundings. Observing this faint infrared light allows scientists to study the hidden workings of planets that remain distant points in the sky. These glowing atmospheres show how energy moves through deep layers of swirling hydrogen and helium, providing a glimpse into environments that dwarf the scale of any weather system on Earth. Tidal interactions can twist stellar envelopes into elongated shapes. When two stars orbit close to each other, their mutual gravity pulls strongly on their outer layers. The tug is not uniform across the star's surface because the near side experiences a stronger pull than the far side. Over time, this uneven pressure shapes the outer region into a form that stretches along the line connecting the two stars. The star becomes slightly elongated rather than perfectly round. This distortion changes gradually as the stars move in their orbits, creating subtle shifts in brightness that reveal the stretching. In some systems, the effect becomes strong enough to influence how the star rotates and how energy moves within its interior. The twisted shape may also alter how the star sheds material or how it exchanges gas with its companion. These interactions demonstrate how gravity can sculpt stars just as it shapes planets and galaxies, leaving behind visible signatures that reveal the forces at work. Some galaxies host enormous cavities where past explosions cleared out vast regions of gas. Within certain galaxies, observations reveal huge hollowed-out areas that appear strangely empty compared to their surroundings. These cavities are thought to form when powerful events release enough energy to push gas outward. Exploding stars, energetic outflows from a central black hole, or bursts of intense star formation can all send shock waves racing through the galactic environment. As these shock waves expand, they sweep away gas and dust, leaving behind large bubbles that remain visible long after the original event has faded. The size and shape of each cavity recalled the history of the forces that created it. Over time, the bubbles may stretch, fragment, or refill as new material drifts inward. Studying these features reveals how galaxies regulate their supply of gas and how energetic events influence future star formation. Each cavity represents a moment of dramatic change that reshaped its host galaxy from within. Interstellar clouds can freeze molecules onto dust grains in icy layers. In the coldest regions of space, temperatures fall so low, but gases behave in unusual ways. Molecules drifting through these dark clouds can become trapped on the surfaces of dust particles. Once attached, they form thin, icy coatings that build up layer over long periods. These frozen layers often contain water, carbon dioxide, methane, and other compounds that remain solid in frigid conditions. As cosmic rays and faint ultraviolet light pass through the cloud, they trigger slow chemical reactions within the ice. These reactions create more complex molecules that enrich the cloud with material that may later participate in the birth of stars and planets. When the cloud eventually collapses, the heat from forming stars evaporates the ice and releases its chemical inventory into the surrounding gas. These icy grains act as tiny storage sites that preserve the earliest stages of chemical evolution in the galaxy. Stellar mass black holes can form when massive stars collapse. A star many times larger than the Sun spends its life fusing heavy elements in its core until the reactions can no longer support its weight. When the outward pressure fails, gravity pulls the core inward with overwhelming force. The collapse proceeds so quickly that the core becomes an object of extraordinary density. If nothing can stop the contraction, the core turns into a black hole with a mass similar to that of the original star, but compressed into a much smaller volume. The outer layers may blast outward in a dramatic explosion, while the black hole remains behind as a silent remnant. Although it emits no light of its own, its presence becomes visible through its effect on surrounding matter. Gas spirals toward it, heating up and producing radiation that can be detected from across the galaxy. These remnants show how the death of a single massive star can produce one of the most extreme objects in the universe. The surfaces of neutron stars contain matter packed at astonishing densities. After certain stars explode, their cores collapse into compact spheres composed mostly of neutrons crowded together more tightly than any material found on Earth. The surface appears solid, yet the matter within it is unlike anything in ordinary experience. At the top, most layer atoms are squeezed into a state where electrons have combined with protons, leaving a crust of neutron-rich material. Deeper within, the density becomes so extreme that the properties of matter remain a subject of active research. The gravity at the surface is so intense that even a small irregularity could weigh countless tons. When these stars rotate or shift, stresses can build in the crust until sudden adjustments release bursts of energy detected as short flashes of radiation. By studying these signals, scientists learn more about the behavior of matter under conditions impossible to reproduce on Earth. Neutron stars offer a unique laboratory for probing the fundamental nature of the universe. Some exoplanets orbit in chaotic systems where gravitational pulls constantly shift their paths. In certain star systems, multiple planets move so closely that their mutual influences never settle into a stable pattern. Each orbit produces subtle tugs that accumulate over time, altering the shape and tilt of the paths each planet follows. The result is a dynamic environment where predictions become challenging, even for advanced models. Some planets may drift slowly inward or outward, while others may change their orbital shapes in cycles that play out over long periods. The interactions can become so strong that one planet may eventually be flung into a new region of the system, or even ejected entirely. Observations of these chaotic systems reveal just how varied planetary architectures can be. They show that not all systems resemble the orderly layout seen in our solar neighborhood. Instead, the galaxy contains environments where gravity produces an ever-shifting dance that never fully repeats itself. Jets from young stars can carve long channels through surrounding gas. As a young star gathers material from its surrounding disk, some of the unfailing gas becomes channeled by magnetic fields and expelled from the poles of the star at high speed. These narrow streams of material travel outward in opposite directions, plowing into the surrounding cloud. Wherever the jets strike, they compress and heat the gas, creating glowing regions that mark the path of the outflow. Over time, the jets push aside large volumes of material, creating elongated cavities that stretch far from the central star. The motion of the jet can vary as the young star rotates or as conditions, and the disk change, producing knots and ripples along the channels. These structures help scientists understand how young stars shed angular momentum and clear their birth environments. The jets reveal both the power of early stellar growth and the complex interactions between newborn stars and the clouds that created them. Ultra-faint dwarf galaxies contain few stars, yet significant dark matter. These tiny galaxies orbit larger systems and appear as faint smudges that require careful observation to detect. Despite containing only a modest population of visible stars, they display motions that indicate far more mass than the stars alone can explain. This hidden mass is attributed to dark matter, which exerts gravity without emitting light. The abundance of dark matter helps the dwarf galaxy maintain its structure, even though its visible components are sparse. By studying the motions of the stars within these faint systems, astronomers gain valuable insight into the distribution and behavior of dark matter on small scales. These galaxies also preserve ancient populations of stars that formed early in cosmic history, offering a glimpse into conditions that prevailed long before the Milky Way took its present shape. Their faintness and simplicity make them vital tools for understanding both dark matter and the early universe. Star formation can stall when intense radiation evaporates surrounding gas. In regions where massive stars ignite their powerful light, floods the environment with heat. This radiation strikes nearby clouds and causes molecules to break apart and drift away. As the gas heats and expands, it becomes too diffuse to collapse under its own gravity. Without this collapse, the process of forming new stars slows or may even stop entirely. The influence extends through large areas, shaping where future stars can appear. Over time, the balance between heating and cooling determines whether a cloud continues to grow dense regions or becomes a largely inactive zone. Observations of these environments reveal complex interactions between forming stars and the material that surrounds them. The struggle between radiation and gravity plays a major role in controlling the pace of star birth across galaxies. Some planets contain seas of liquid hydrocarbons instead of water. On certain frigid worlds far from their stars' temperatures fall so low that substances familiar on Earth as gases can condense into flowing liquids. Methane and ethane, which drift invisibly through our own atmosphere, become dense enough to pool into lakes and seas. These bodies of liquid spread across broad basins, carved over millions of years by rainfall that consists not of water, but of hydrocarbon droplets. The surrounding landscape may feature channels etched by rivers that carry these liquids toward larger basins, forming coastlines. Shaped by exotic weather cycles, clouds of hydrocarbons gather in the sky, release storms, and refill the lakes in repeating patterns. The chemistry in these environments is rich and complex because carbon-based molecules behave differently under such extreme cold. Researchers believe that reactions occurring at these low temperatures could create compounds not easily formed in warmer climates. These alien seas reveal that worlds can host active climates even when sunlight is faint and water is locked away as ice. Gamma-ray bursts can unleash colossal amounts of energy in a single moment. These astonishing events occur when certain stars reach the final stages of their evolution and collapse into compact remnants, or when two dense stellar corpses merge. The resulting explosion releases a concentrated flash of high-energy radiation that sweeps across the cosmos with extraordinary brightness. For a brief period, the burst outshines entire galaxies, even though the source may be no larger than a stellar core. The radiation travels outward along narrow paths, and if one of those paths happens to align with Earth, astronomers detect a brilliant flare that lasts from fractions of a second to several minutes. The afterglow continues for days or even weeks as the expanding shockwave interacts with surrounding material. These bursts provide insight into the most extreme physical conditions known, including intense magnetic fields and rapid particle acceleration. Observing them helps scientists understand how heavy elements disperse across galaxies and how violent events shape the evolving cosmos. Some asteroid families share a common origin in ancient collisions. Long ago, countless rocky bodies moved through the early solar system on intersecting paths when two sizable asteroids collided. The impact shattered them into numerous fragments that scattered into new orbits. Over time, these fragments continued to travel around the Sun, gradually spreading into clusters that maintain similar compositions and trajectories. By studying the colors, reflectivity, and motions of these bodies, scientists can group asteroids into families that reveal the nature of their long-vanished parent objects. These families preserve information about the conditions that shape the early solar system and the types of materials present during planet formation. The study of these related fragments helps researchers trace the timeline of ancient impacts and understand how collisional processes influence the distribution of material that eventually became moons, planets, sea, and comets. Even today, these families continue to evolve as gravitational interactions nudge their members into new paths. Planetary magnetic fields can trap charged particles in giant glowing belts. When a planet possesses a strong magnetic field, the field extends outward into space and forms an invisible structure capable of guiding charged particles. Solar wind and cosmic rays often supply these particles, which become captured and spiral along magnetic lines. As the particles collide with atmospheric molecules or interact with the magnetic field itself, they release energy in the form of faint light that can encircle the planet in broad toroidal regions. These belts can shift and brighten when bursts of stellar activities send waves of additional charged particles into the system. The behavior of the trapped particles reveals details about the strength and shape of the magnetic field. Studying these belts helps scientists understand how magnetic shielding influences planetary habitability. Because strong fields can protect worlds from harsh radiation, the glowing regions demonstrate how magnetic forces create dynamic structures that surround planets and influence their long-term evolution. Relativistic effects near black holes can distort the passage of time. As an object approaches a region of intense gravitational pull, the fabric of space-time stretches in ways that affect how time flows. Observers far from the black hole see the approaching object slow gradually, as if its motion becomes frozen, near the boundary where escape becomes impossible. Meanwhile, for the object itself, time continues normally, even though external events appear to speed up dramatically. The differing perceptions arise because gravity influences not only spatial trajectories, but also the rate at which time progresses. These distortions grow stronger as the distance to the black hole decreases. Instruments that measure signals from matter spiraling inward detect shifts but confirm this slowing of time. Understanding these effects is essential for studying how black holes interact with their surroundings and how gravity shapes the universe at its most extreme. They reveal that time is not a fixed background, but a dynamic quantity influenced by mass and motion. Some galaxies rotate around invisible concentrations of dark matter. Although these galaxies contain stars' gas and dust, they're visible. Components alone cannot account for the speeds at which they rotate. Instead, an unseen mass exerts additional gravitational influence, holding the galaxy together despite its rapid motion. This hidden mass forms a halo that surrounds the visible disk and extends far beyond its outer edges. The stars orbit within this halo, following paths shaped by the distribution of dark matter rather than solely by the luminous material. Observations of rotation curves reveal that the gravitational pull remains strong even where visible matter becomes scarce. By mapping these motions, astronomers infer the structure and density of the dark matter that dominates the galaxy's mass. Although dark matter does not emit or absorb light, its effects on the dynamics of galaxies provide crucial clues about the composition of the universe and the processes that govern cosmic evolution. The atmospheres of some exoplanets contain clouds made of vaporized minerals. In extreme environments close to their stars, temperatures soar high enough to vaporize rock. Minerals that remain solid on Earth turn into gases and rise into the upper atmosphere, where they condense into clouds of tiny droplets or crystals. These clouds form intricate layers that vary with altitude, temperature, and chemical composition as the planet rotates. Winds carry the mineral-rich vapors across the sky, producing variations in brightness that shift with the orbital phase. Observing these changes allows scientists to study the mineral content of the atmosphere and model the conditions on the planet's day and night sides. Such exotic clouds demonstrate the extraordinary diversity that exists in planetary atmospheres across the galaxy. They show that even familiar elements can behave in surprising ways under different temperatures and pressures, creating skies unlike anything found within our solar system. Starquakes can rattle the surfaces of neutron stars. These compact stellar remnants have crusts that behave like rigid surfaces resting atop oceans of extraordinarily dense matter. As the star rotates or undergoes internal changes, stresses accumulate in the crust. When the stress becomes overwhelming, the crust shifts suddenly and releases energy in a seismic event that resembles an earthquake. These starquakes send vibrations through the entire object and can produce flashes of high-energy radiation detectable across great distances. Some quakes also alter the rotation of the neutron star, slightly creating measurable changes in the timing of its pulses. By studying these events, scientists gain insight into the internal structure of neutron stars and the behavior of matter under extreme pressure. The quakes reveal how the dense surface responds to ongoing changes within the star, offering clues about phenomena that cannot be replicated on Earth. Some stars are so massive, but they fuse elements up to iron in their cores during their lifetimes. These enormous stars burn through their fuel at astonishing rates, progressing rapidly from hydrogen to helium, then to heavier elements. As the temperature and pressure in the core rise, fusion reactions produce carbon, oxygen, neon, and other intermediate elements. Eventually, the core becomes hot enough to fuse silicon into iron. At this stage, energy production reaches a halt because fusing iron does not release energy. Without a fresh supply of outward pressure, the core collapses, leading to a catastrophic explosion that scatters the star's material into surrounding space. The heavy elements created during this final fusion cycle contribute to the chemical richness of the galaxy. By observing these massive stars at different phases of their evolution, scientists learn how they shape cosmic environments and provide the raw material for planets and future generations of stars. Distant planetary systems can contain icy bodies far beyond their giant planets. Far from the warmth of the central star, temperatures fall to levels where water, methane, carbon dioxide, and other volatile substances freeze into solid form. These remote regions often host populations of icy objects that orbit quietly and rarely interact with the inner system. Their surfaces remain unchanged for long periods, preserving clues about the earliest stages of planetary formation. When scientists detect these distant bodies, they analyze their orbits to learn how the system evolved and whether giant planets migrated during its youth. The distribution of icy material helps reveal how disks of gas and dust developed around young stars. By comparing remote objects in various systems, astronomers gain insight into how common such outer reservoirs are and how they influence the potential for comets, moons, and other icy wanderers to form. These distant bodies enrich our understanding of planetary diversity across the galaxy. The faint glow between galaxies contains the afterglow of ancient stars. In the vast spaces separating galaxy clusters, a delicate light lingers that is almost impossible to detect without sensitive instruments. This glow arises from stars that were stripped from their original galaxies during past collisions and gravitational interactions. As galaxies passed one another, all merged, some stars were flung into intergalactic space, where they continued shining in isolation. Over time, many of these stars dimmed, aged, and eventually faded. Yet their combined light forms a soft radiance that fills the darkness between clusters. This glow holds clues about the history of galactic interactions, because the number and brightness of the stray stars reflect how often galaxies collided, merged, or cannibalized their neighbors. By analyzing this faint emission, astronomers reconstruct events that took place over billions of years. The light becomes a quiet record of cosmic history, revealing the long and intricate journeys of stars that now drift far from any galaxy. Some comets release jets of dust and gas as they approach their stars. These icy wanderers spend most of their lives in remote regions where temperatures remain extremely low. As they move inward toward the warmth of the star, sunlight begins heating their surfaces and penetrating their outer layers. The trapped ices vaporize, building pressure beneath the crust until they burst outward through cracks and weak points. The jets carry dust gas and icy particles into space, forming bright comas that surround the nucleus. These outflows can rotate, pulse, or shift depending on how the comet spins and how sunlight strikes its surface. The material expelled by the jets contributes to the formation of long tails that point away from the star. Observing the behavior of these jets offers insight into the composition and structure of the comet's interior. They reveal how volatile compounds respond to heating and how ancient materials, preserved since the solar system's birth, return briefly to visibility before fading once more into the cold. Galactic winds can blow gas out of galaxies and quench star formation. In regions where many massive stars form and die in rapid succession, powerful outflows of energy arise from their combined activity. Supernova explosions, intense radiation, and fierce stellar winds push surrounding gas outward with tremendous force. This material can escape the gravitational pull of the galaxy, reducing the supply of cool, dense gas needed to form new stars. Over time, these winds may reshape the structure of the galaxy, creating large cavities and sweeping channels that mark the pathways of the escaping material. The loss of gas slows the birth of new stars and may eventually bring star formation to a near halt. Observing these winds helps scientists understand why some galaxies remain active while others fade into quieter phases. The presence of such wind demonstrates how feedback from stars influences the long-term evolution of galaxies and regulates the balance between creation and destruction within them. Some stars wander the galaxy at high speeds after gravitational encounters. During close interactions with clusters, binary companions, or spiral orange stars can receive sudden boosts of velocity that send them racing across the Milky Way. These encounters occur when gravity from multiple sources acts in just the right way to accelerate the star. In extreme situations, the star may be propelled so strongly that it escapes the galaxy entirely and becomes a solitary traveler in intergalactic space. Even when the speed is not high enough for escape, the altered trajectory can carry the star far from its birthplace. By tracing their paths backward, astronomers identify the crowded or unstable regions where these stars originated. Their unusual motions reveal details about the gravitational landscape of the galaxy and the interactions that shape stellar populations. Each wandering star becomes a messenger carrying information about the dynamic forces that govern motion within the Milky Way. The surfaces of some exoplanets may be covered in oceans of molten rock. On worlds that orbit very close to their stars, temperatures rise high enough to melt the upper layers of the crust. The result is a shifting sea of liquid rock that glows with intense heat. These magma oceans can extend across entire hemispheres or wrap around the planet, depending on rotation and heat distribution. Gas is released from the molten surface, form atmospheres filled with vaporized minerals that condense into glowing clouds. Winds carry these vapors to cooler regions where they solidify and fall back as mineral-rich rain. The boundary between molten and solid terrain shifts continually as the planet rotates, creating dramatic temperature contrasts between the scorching day side and the cooler night side. Studying the light emitted by these planets allows scientists to infer the composition and temperature of their molten surfaces. These extreme environments demonstrate how closely a planet can approach its star before its geology is transformed into a dynamic ocean of rock. Supernova remnants can contain swirling knots of highly enriched gas. After a massive star explodes, the expelled material expands into the surrounding space in a complex, mixture of shockwaves and glowing debris. Within this expanding cloud, clumps of heavy elements form as the gas cools and interacts with itself. These knots contain elements forged in the star's core or produced during the explosion, making them pockets of material that differ significantly from the surrounding gas. As the remnant grows, its filaments twist into intricately shaped structures, each glowing at specific wavelengths that reveal its elemental composition. Scientists study these knots to understand how supernova distribute heavy elements throughout galaxies. These materials eventually become part of new stars' planets and even the building blocks of life. The presence of these enriched regions shows how the death of one star contributes to the chemical diversity of future generations. Some galaxies harbor enormous amounts of cold molecular hydrogen. This invisible gas forms the raw material for star formation, yet it emits very little detectable radiation at typical interstellar temperatures. Instead, astronomers identified by observing the faint emissions from molecules that accompany it, such as carbon monoxide. In certain galaxies, especially those undergoing rapid growth, vast reservoirs of cold hydrogen remain hidden until detected through careful surveys. These reservoirs can extend across large regions and fuel waves of star formation that last millions of years. The presence or absence of this cold gas determines whether a galaxy will continue forming stars or enter a quieter stage. By mapping whether gas resides, scientists gain insight into the processes that drive galactic evolution, from mergers to internal dynamics. This hidden component of galaxies plays a central role in shaping their behavior across cosmic time. Stellar collisions can create unusually massive and luminous stars in crowded environment, such as the cause of dense clusters. Stars may pass so close to one another that their outer layers merge. If the collision is gentle enough, the stars combine into a single object with far greater mass than either possessed previously. The new star becomes hotter and brighter because its increased mass allows it to fuse elements at a more rapid rate. These collision-born stars stand out among their neighbors due to their intense blue light and surprising youth compared to the surrounding population. Observing them provides insight into the dynamic interactions that occur in dense stellar environments. Their existence demonstrates that not all stars form from simple gravitational collapse. Some emerge from the violent but creative encounters that take place in the crowded realms of clusters. Some planets experience extreme temperature swings between day and night. Planets orbiting close to their stars may rotate slowly or become tidally locked so that one side always faces the star, while the other remains in perpetual darkness. The day side heats to scorching levels, while the night side cools to frigid temperatures. Between the two hemispheres lies a region of dramatic gradients where intense winds attempt to redistribute heat. The atmosphere circulates rapidly, carrying warm material toward the night side and returning cooler gases toward the day side. These patterns create complex climates that vary with altitude, cloud formation, and atmospheric composition. Observing these temperature contrasts allows researchers to infer how energy moves through the atmosphere and how stable the climate might be over time. The extreme differences between day and night conditions reveal the diversity of environmental conditions that planets can host even within the same system. The outer edges of some galaxies contain stars that barely orbit at escape speed far from the bright central regions. The gravitational pull of the galaxy weakens, and the stars in these remote outskirts travel more slowly than those closer in. Yet the presence of dark matter creates a gravitational field strong enough to keep them bound, even at great distances. Some stars move along wide paths that take them to the limits where the galaxy's pull almost fails. Their motions help map the extent of the dark matter halo that surrounds the visible galaxy. By analyzing the speed and distribution of these remote stars, astronomers gain crucial information about how galaxies grow and how unseen mass shapes their structure. These quiet outer reaches serve as a frontier where the visible and invisible components of the galaxy meet, creating a boundary that reveals the true scale of galactic influence. Some black holes emit soft X-rays as matter spirals inward. Although black holes themselves produce no light, the material swirling around them forms a brilliant display that radiates across many wavelengths. As gas from a nearby star or cloud drifts toward the black hole, it accelerates and compresses into a thin disk heated to millions of degrees. The inner regions glow intensely, often releasing a gentle but detectable form of X-rays, known as soft X-rays. These emissions help scientists study conditions close to the point where gravity becomes overwhelming. The pattern and strength of the radiation reveal how quickly matter is falling inward and how the disk is structured. Variations in brightness can indicate turbulence, magnetic disturbances, or changes in the supply of nearby gas. Observing these soft X-rays provides rare insight into environments that lie just outside the boundary where escape is impossible. They offer a window into the final moments of material that is about to vanish from view forever. Complex organic molecules can form in cold, dark nebulae within the deepest reaches of interstellar clouds where starlight barely penetrates. Temperatures drop low enough for exotic chemistry to unfold slowly over long periods. Dust grains coated with thin layers of ice serve as tiny laboratories where atoms gather and react. Cosmic rays and faint ultraviolet light can penetrate these shadows, just enough to trigger interactions between molecules trapped in the icy coatings. Over time, these reactions produce intricate organic structures that include chains, rings, and branching arrangements of carbon-rich compounds. When the nebula begins to collapse and warm, the ice evaporates and releases these newly forged molecules into the surrounding gas. Though presence enriches the material that will eventually form stars and planets, detecting these compounds in cold clouds provides evidence that the basic ingredients needed for biological chemistry can arise long before any planets exist. These dark regions reveal that life's building blocks may begin assembling in the quietest corners of space. Some exoplanet atmospheres expand into huge puffy envelopes in extreme environments. Where a planet orbits close to a bright star, the intense radiation heats the outer atmosphere until it swells dramatically. The expanded gas becomes so diffuse that it extends far from the planet's surface, forming an inflated envelope, shaped by stellar winds and gravitational pull. These envelopes can grow larger than the planet itself, by many times creating structures that resemble drifting clouds. Rather than compact atmospheres, the gases may escape slowly into space, creating long trails of material that follow the planet along its orbit. Observing the absorption of starlight during transits reveals how these extended atmospheres differ from more compact ones. The size, composition, and temperature of the envelopes provide clues about the planet's history and how strongly it interacts with its star. These swollen atmospheres showcase the dramatic effects of heating in close orbit. Conditions and expand our understanding of how planetary atmospheres respond to extreme radiation. The earliest galaxies formed when the universe was still young and chaotic. In the first few 100 million years after the birth of the cosmos, matter clumped together under gravity to create the seeds of future galaxies. These early structures were small, irregular, and filled with rapidly forming stars whose intense radiation reshaped their surroundings. Collisions between young galaxies occurred, frequently mixing gas and triggering bursts of star formation that burned through material at astonishing rates. The universe at this time lacked many of the heavy elements produced by later generations of stars, so the earliest galaxies contained pristine gas that behaved differently from the enriched clouds found today. Observations of distant galaxies allow astronomers to peer back through time and study these early stages.